Hi, I'm Jeff Bier from the Embedded Vision Alliance. I'm here today with Michael Tusch of Apical. Hello, Michael.
Hi, Jeff.
We haven't spoken in a while for the Embedded Vision Alliance website. I know there's been a lot going on at Apical. I'm interested in catching up with you. Apical is really known for the front-end image signal processing, hardware and algorithms for making beautiful pictures out of maybe less than optimal sensors. But I understand lately you and your team have been working on computer vision, on image understanding algorithms as well. So can you tell us a little bit about that?
Sure, yeah. Well, in fact, we've been working for about the last couple of years on developing our own computer vision engine. And the reason we've done that is we figured that perhaps our knowledge of image processing might be helpful in building a computer vision engine, and we might be able to bring something new to the community in that area. So that's really what we've been doing, and in fact we're demonstrating the first version of that engine here at the Embedded Vision Summit tomorrow.
That's really exciting. So first of all, let's just get some definitions clear. When you say image processing versus computer vision, sometimes the boundary between those two is a little fuzzy. So at least for purposes of this discussion today, what's the distinction between those two things?
Yeah, so image processing is all about taking the raw data that comes out of a sensor and turning it into something that looks natural. In other words, a video that you would watch on a display. And therefore it runs through a large number of stages to get colors right, to adjust noise, to convert the raw pixels to visible pixels. And it's really all about visualization. Whereas computer vision or embedded vision is about taking that same raw data and extracting information out of it. For example, detecting objects, people, faces. And so really that's the difference we were talking about.
So the way you've described it, it sounds like the two are really independent. The image processing is about making images that would be attractive to human viewers, and the computer vision or embedded vision, that's about extracting information about the content, about the meaning of the images. But from your earlier comment, it sounds like maybe they're not completely independent. So how do the two relate?
Yeah, well, I mean, obviously they're both acting on the same data. It's the same raw data streaming out of the sensor that is going both into the image processing engine and the computer vision engine. And when we started, we really wanted to ask ourselves, what's the right way to do computer vision? Is it to take the raw data directly from the sensor, or is it to run it through an ISP and process that data? And there are arguments for and against those. In fact, we've come to the conclusion, and this is how we've really implemented our system, that the best way to do computer vision, if you can, is act directly on the raw sensor data. That's where the data is most predictable and where it has the most information content. And indeed, image processing engines can sometimes wreck that data. Some of the things you do to an image to make it look nice can actually affect your analytics negatively and unpredictably. On the other hand, what we've found is a lot of the techniques we use in the image processing part are very useful within the computer vision engine. So even though these can be regarded as two somewhat independent and parallel engines, by allowing them to communicate with each other and taking information that we gather through our image processing, we're able to make a significant improvement in the accuracy of our computer vision. And that's the particularly interesting result I think we found from this exercise.
That is really interesting. So let's first have an example of the case you described where the front-end image processing actually gets in the way of the computer vision.
Well, if you think about it, computer vision is often based on understanding things like edges. What image processing does is takes the raw data to the sensor and runs it through a whole sequence of nonlinear and adaptive transforms. So it's changing the levels of brightness and color dramatically from the original. And that's very important because actually raw sensor data doesn't have true colors, it doesn't have correct dynamic range. Indeed, it only has one color per pixel. That all has to be reconstructed from the data. So it's doing a lot to the data to shift things around, and not only is it shifting them around, it's doing it in a totally unpredictable way. So if you just receive video from a camera without any knowledge of how it's been created, you really have no knowledge of the original data that's come from the sensor, and that tends to be what we need to use for computer vision.
Very interesting. So then talk about the other aspect of this that you mentioned a minute ago, which is how bypassing that sort of processing, the normal front-end image processing that would be done to make a pleasing looking image, bypassing that, but and operating on the raw sensor data, but using sort of meta information about the raw data can enable you to do a better job of computer vision.
Yes, there's a whole range of pieces of information that are useful to the computer vision engine, which isn't typically available to it. So, in a classic situation where we're doing post-processing of video data, as I mentioned, there's a lot of information that's been acquired by the camera and then discarded because all that's needed is the visible output. One very good example of that is noise analysis. So, we all know that as you take a camera into a darker room, it gets noisier. And obviously noise is going to make it more difficult to detect things. It's kind of intuitive, but exactly how and why that happens is quite an interesting topic, and actually I'm going to be talking about that tomorrow. And what we find is if we do what we do in image processing, which is we characterize the sensor and we model the way it behaves under different lighting conditions, we can accurately predict the noise levels in any scene and use that when we do our computer vision. So for example, you can imagine that your robustness towards false positives and false negatives can be quite significantly informed by the noise levels in the scene. And because we have that information accurately extracted by the image processing engine, we can use that. And in fact, in our tests, we can have significant improvements in detection accuracy just simply by knowing how noisy the scene is. Not by reducing it or changing it, just by knowing.
So the front-end image processing steps, instead of trying to hide the noise, which would be the normal thing you would do if you were trying to produce an image for human consumption, they're instead characterizing the noise, passing that information to the vision algorithms to assist those algorithms in doing a better job of detecting objects or something like that?
Correct, that's exactly right.
Very interesting. So in thinking forward then in an application like a smartphone where it's going to be called on to do, camera's going to be called on to do both things, right? Capture beautiful images, but then also recognize faces and road signs and that sort of thing. How do you envision this working? Will there be a sort of mode to bypass the ISP, the normal image beautification steps, and say, don't reduce the noise, don't correct the colors, don't do all those other things. Instead, give me some statistics, which I'll use for downstream vision processing. And how do you envision this being implemented?
I think one of the things I've picked up from coming to these regular meetings that we have is that in future, I think all cameras are going to be smart. I think every camera, including smartphone cameras, is going to have a substantial amount of computer vision in it. And the way I see it is that you're going to have a sensor at the front, and that data is just going to be split, and it's going to run through an image pipe to produce beautiful images, and it's also going to run through a computer vision pipe to produce information about the scene. And these two things are going to help each other out. As I mentioned, the image processing engine is going to help out the computer vision engine. There's a number of examples, but noise is one. Of course, the computer vision engine is going to help out the camera, the imaging part. I mean, we all know that cameras use face detection to help them with exposure and focusing. But if we've got a genuine computer vision engine that can extract real information about the scene, we can use that to improve the performance of the camera in many ways and make it closer to what we see with our eyes. Solve some of the problems that still occur in cameras. Even the best smartphones still have trouble getting the right colors under some conditions, still will overexpose, still will find it difficult to focus. And so I think these two engines working in tandem is how it's going to be in the future.
That's pretty interesting. So two streams coming out of the image pipeline. The sensor feeding these two engines, one outputting improved images for human consumption, the other outputting kind of object detection type information, which it produces operating on the raw, unbeautified images, but with benefit of some statistics about the captured sensor data.
That's right. I think the smartphone is a very good example of that kind of system. I think we can also imagine other kinds of new sensors coming out, which don't actually require any visualization. You could imagine what we would traditionally call a camera, which is basically a lens, a sensor, and some kind of back end, which doesn't actually need to output any video. It might only want to output what it knows about the scene, for example, where objects are and how they're moving. And so that could perhaps change the landscape somewhat, because of course there's a lot of infrastructure that has to be put in place to transmit video. Encoders, decoders, a lot of bandwidth, storage. If we can put more intelligence into the camera, in many situations we may find we don't need to transmit all that data. So I think that's the other aspect of working directly on the sensor data, as opposed to the requirement of putting through an image processing engine.
Very interesting. So you said that Apical's been developing a computer vision engine. What's the status of the development of that product?
Well, it's working, which is good. So,
congratulations.
It was working when I looked a few minutes ago in the demo. So where we are is we've implemented a complete vision system and image processing system on a Xilinx Zinc part. And we followed a similar approach to what we've done very successfully for image processing, and really that's to do a lot of the pixel processing in dedicated hardware. And that's perhaps a little bit different to some of the other approaches that we see going on, and it of course has advantages and disadvantages. But one of the big advantages of doing a lot in really dedicated silicon is that we can operate at very high data rates with very high accuracy. So for example, the system we've got is running on full HD 60 frames per second video, and we're not rescaling, we're not skipping frames, we're processing every pixel of every frame. And what that allows us to do is, we're illustrating people tracking and detection. We can detect any number of people in any orientation, any size scale. So the combination of a hardware-based front end together with what we have is a whole bunch of embedded firmware running on the ARM core, gives us actually quite a powerful computer vision engine. And when we put that alongside the image processor, I think the results are pretty impressive in terms of what we can do.
That's really interesting. So is the FPGA the deployment platform for this, or is it a demonstration and prototyping platform, and is your ultimate intent to deploy this as silicon IP to be integrated into SoCs?
Yes, I think both, actually. Again, following our experience with image processing, we tend to develop our new designs on FPGAs, and we also find that we deploy those in the market on FPGAs initially with early adopters. Those are the kind of companies that are really looking to have the latest performance, and the volumes are maybe actually quite high, but thankfully the FPGA price points are about right for many of those devices. But then what we do find is once that technology becomes stabilized, we usually follow a path of silicon integration into an SoC. And in fact, our designs are common to both. I mean, the design we implement on Zinc is virtually identical to what we'd implement on an SoC. So I think we can see both of those paths coming from this.
Very interesting. So, what do you expect to be the first applications where this computer vision engine will be deployed?
Yeah, I mean, it's got wide applications, but again, we thought we'd try and set ourselves more modest goals initially and see if we can get it working well, and then try to go more broadly. And the initial goal we set was to be able to track people continuously within indoor environments, so in a room. Now that makes life a lot easier because lighting's not too variable and the background doesn't move around too much, and so on. And what we do now is find that we can very successfully do that. And there are a whole bunch of applications for where you want to be able to analyze where people are in an indoor environment, and that's really what we're aiming at the moment. Once we get that right, we'll, I think, start looking at more general environments, outdoors, variable lighting conditions, and so on. But,
interesting. Now, because you have dedicated logic implementing these algorithms, I assume this means that you're not expecting your customer to reprogram your engine with different algorithms. Is that right?
Well, yes and no. I mean, what we identified, and actually this also came from being part of this community that you've set, is really that there's there's clearly emerged a set of basic algorithms that underpin most object detection algorithms today. And those are fairly well defined. And those are also happen to be the most costly in terms of computational resources to do. On top of that, so what we do is we build them in hardware. Now they're all reprogrammable. For example, in our current system we have a total of 16 classifiers, and those can be trained for just about any kind of rigid object you want. So when we detect a person, we're actually detecting that person through a combination of different head positions, different upper body positions, and different full body positions, and each one of those is a classifier, and each one of those is trained via a big training set offline, and then that's loaded in, and that's actually reprogrammable. So the engine can be reprogrammed to detect road signs or animals or whatever. So there's a reprogrammability built in, even though the hardware engine that does it is fixed. And then of course on top of that, what we do is we take that data, that classified data, and then we have to post-process it, and then we have to figure out, is there actually a human there, and which direction are they moving, and what are they doing? So there's a combination of hardened algorithms and also flexibility in the software stack above it. And again, we think that's the right split. Time will tell if that's correct, but that's our approach.
Really interesting. So you mentioned a presentation you're going to be giving here tomorrow at the Embedded Vision Summit. I'll let our viewers know that presentation will also be available on the Embedded Vision Alliance website, and we'll put a link next to this video pointing to that video. So my understanding is you're going to get into more of the technical grounding for using image processing statistics to inform vision algorithms in your Embedded Vision Summit presentation tomorrow. Is that right?
That's right. Actually, I'm going to show some results we gathered from our own experiments, where we were trying to quantify from our own point of view what were the benefits, for example, of including noise statistics in a computer vision algorithm. And we've got some good data, and I think it should be hopefully interesting to people involved in this to see. I think this kind of analysis isn't usually thought about. I think most people who work in computer vision who are trying to improve the accuracy of their detections are thinking entirely about the algorithms of computer vision. And in fact, there's a lot that can be done even before you get to that point. And that's really our interest in how do we get, it's a total solution. You could even argue that your choice of lens has a big effect on the success of your computer vision algorithms. So we'd like to think of it all together. And we've got a good platform to do that, actually. And so, hopefully some of these results may be of interest.
Well, it's a really good reminder that vision systems do tend to be, sort of multidisciplinary, multi-technology systems, and, you probably get the best result by sort of co-optimizing, whether it's optics, sensor, algorithms, lighting, whatever, co-optimizing all together. If you're just hammering away on one piece, leaving everything else constant, you can probably make improvements, but maybe that's not going to be your best path to
that's right, especially if your bottleneck is somewhere else in the system. And also if you're under cost constraints, which every system is. So in an ideal system we might not have to worry about the quality of the optics or the quality of the sensor or even the quality of the image processing, but in reality we have to deal with these constraints, and therefore an understanding of what happens as you play with these different variables is obviously quite important if you want to control the quality of the final output, which is really what matters here.
Makes really good sense. Well, I'm really looking forward to your presentation tomorrow at the Embedded Vision Summit. Thanks very much for taking the time to talk with me today. If people want more information about this new product from Apical, this Vision Engine, where can they get that?
Yes, well, it is new, so we've got some information on our website, but it's early stage. So we're going to be putting more information on the website over the coming weeks. We're going to be putting some white papers and some examples up there, and we'll also hopefully be putting some more material on the Embedded Vision website as well. So watch this space.
Excellent. Thanks very much, Michael. Great talking to you as always.